How do you calculate the pH of a buffer solution? The nice thing about buffer solutions is that when you mix, if you have a source of an acid, a weak acid, and a source of its conjugate base. So here's an example where you have 0.5 moles of acetic acid, and you mix it with half a mole of sodium acetate, and you make up a solution. The nice thing about buffer is that because you have comparable amounts of conjugate acid and base, okay, they tend to suppress each other's ionization. So for practical purpose, you say at equilibrium, provided there you have comparable amounts, at equilibrium, whatever starting amount you have is going to be the same. So for example, HX, what do we know about HX in water? It gives you H plus X minus, right? So if you start off with 0.5 moles of acetic acid per let's say per liter, okay, then but you also have 0.5 moles per liter of X minus, okay, then this ionization is going to be suppressed because of the presence of the conjugate base. The same thing with the conjugate base. Its ionization in water, which will give you HX plus hydroxide. You can think of it this way. If you have 0.5 moles per liter of your base and 0.5 moles per liter of your acid, okay, the ionization of your base is suppressed by the presence of the acids. So pretty much whatever starting amounts you have at equilibrium, that will still be the same amounts if you can see that you've got comparable amounts. And now what did we say are comparable amounts? Anywhere between 0.1 and 10. Okay, so to solve this problem is fairly simple. Okay, so you just say, okay, this is the actual concentration here is going to be 0.5 over whatever the volume is, right? Since you're given the mole, so you have to have concentration. So your equilibrium concentrations is going to be 0.5 over V for acetic acid, and for your acetate, sodium acetate, so this is the conjugate base, acetate, C2H3O2 negative, and acetic acid is HC2H3O2 HC2H3O2, okay? So that's this is what we're referring to as HX here, and that's your X minus. So the concentration of your conjugate base is also 0.5 over total volume. And let's be more precise here. Let's put the right number of sig figs that are given in the question. All right. So what would be the concentration of H plus? You know that Ka is equal to H plus times X minus over HX, right? So you can say that's going to, you can solve for H plus if you're interested in the pH, correct? So how do we solve for H plus? Let's rearrange this. You can say that H plus equals Ka times Hx over X minus. Do we know what our Ka is? Our Ka is not given, but we're given the pKa. It's 4.74. So that is 10 to the negative pKa. Okay, so Ka would just be 10 to the negative pKa. And Hx is how much? X minus is 0.5 moles over the volume. Okay. And your X minus concentration is also 0.5 moles divided by the volume. Okay. So it doesn't really matter what the volume is, right? It just cancels out. And so 0.5 over 0.5. That's 1. So this is just 1. So this is a 1:1 buffer, we say. The ratio of the conjugate base to acid is 1:1. So what's our Ka here? What is our H plus here? It's just 10 to the negative pKa, right? Since this is 1 times 1. So what's our H plus? What is our pH? pH would be log of 10 to the negative 4.74. It's just a negative log. It's just negative of negative, so it's positive 4.74. If the ratio is 1:1, pH will just be equal to pKa. If the ratio is 1:1. Okay? And you'll find that if the ratio is 10:1, okay, or 1:10, then your pH is either, it's going to be anywhere between pKa plus 1 or pKa negative 1. In other words, the useful range for a particular conjugate pair would be within 1 unit of its pKa. Okay? So that's what you'll find if you did that. Let's take a look at, let's look at another way. Let's look at this another way, okay? If you have Ka equals H plus times X minus over Hx, then you can say, if you take the log, negative log of both sides, you can say negative log of Ka equals negative log of H plus, okay, plus negative log of base, which would be X minus over acid Hx. So I'm just taking the log of this, okay, this expression down here. But what is negative log of Ka? That's pKa. So that's equal to negative log of H plus, which is pH, minus log of base over acid. Okay? And so let's rearrange this to solve for pH. Then you can say pH equals pKa plus log of base over acid. This equation right here is a very, very useful equation for quick calculation of pH if you know the pKa and you know the base to acid ratio. Okay? So pKa here plus or minus the base to acid ratio. This is called the Henderson-Hasselbalch equation. It's really this, you know, just what's the word? Another way of writing your expression for Ka. So you really don't need to memorize this, but this just happens to be a convenient equation to use when we're dealing with buffer questions. Why? What happens if the ratio is 1? Then you can say pH equals pKa plus log of 1. What's log of 1? 0. So pH equals pKa. Okay? What happens if the ratio is 10? So what if X minus over Hx is 10? Then your pH will be pKa plus log of 10. What's log of 10? 1. See? What happens if the ratio is 0.1? X minus over Hx equals 0.1. Then your pH is going to be equal to pKa plus log of 0.1, which is going to be negative 1, right? So you would expect your pH then to be, okay, pKa minus 1. All right, so if you know the pKa of your weak acid, then the buffer that you can expect to make from that has to have a pH that's somewhere between pKa minus 1 and pKa plus 1 for it to be a good buffer. Okay? It works best that way. All right. So what's the range of pH values for an acidic acid sodium acetate buffer if the pKa of acetic acid is 4.74? Well, if it's 4.74, that's 4.74 plus 1, 5.74. 4.74 minus 1 would be 3.74. So you can use acetic acid and sodium acetate as a buffer if the pH that you want to stabilize, the desired pH that you want is between 3.74 and 5.74.